The universe is not merely a collection of galaxies with familiar spiral or spherical shapes. Some galaxies exhibit strange and extraordinary forms, as if painted by the creative hand of nature. What has shaped these extraordinary structures, and what do they reveal about the dynamics of the universe? In the vast universe, galaxies appear in a wide variety of shapes and sizes. However, some stand out with their unique forms, becoming wonders amidst the expansive cosmic canvas. These extraordinary structures are not just peculiar physical phenomena, but also critical pieces that help us better understand the movement and evolution of the universe. Ring galaxies are among the most distinctive galaxy types. Their appearance, like a radiant ring in space, is often the result of a strong gravitational collision between galaxies. When a smaller galaxy passes through the center of a larger one, the interaction creates shock waves that ripple through the galactic disk, triggering intense star formation along the ring. This results in a ring of fire, where millions of young, hot stars are forming. A prime example is the Cartwheel Galaxy, located about 500 million light-years from Earth. With its wheel-like shape, the Cartwheel Galaxy captivates attention with its bright outer ring filled with young stars, contrasting beautifully with the inner core, which contains older stars. Additionally, distorted galaxies exhibit equally unusual shapes. These galaxies lose their balanced structures due to interactions with nearby galaxies or powerful collisions. Their spiral arms are often stretched asymmetrically or even completely deformed, creating forms that resemble a moving painting in space. For instance, the antennae galaxies, NGC 4038 and NGC 4039, which resemble two antennae touching, vividly demonstrate the merger of two galaxies. This process not only distorts their original structures, but also triggers starburst events as gravitational forces compress interstellar gas clouds. Galaxies with such unusual shapes are not only visually striking, but also serve as valuable historical records, helping scientists decode the events that shape the universe as we see it today. They allow us to glimpse into the past, when galaxies interacted and collided in a universe that is always in motion. By studying these galaxies, we can gain deeper insights into the role of gravity in forming and evolving large-scale structures and predict the future of galaxies and their planetary systems. When galaxies interact, the universe becomes a grand stage where gravitational dances are performed over millions of light years. This process is not merely the influence of gravity, but also a driver of incredible transformations, from shape distortions to the creation of new galactic structures. Interactions between galaxies are vivid demonstrations of the universe's power and dynamism. Gravitational interactions between galaxies not only draw them closer, but also induce dramatic changes in their shapes and structures. These forces can stretch spiral arms, push dust and gas into galactic cores, or even tear stars away from their parent galaxies, forming delicate streams of material stretching hundreds of thousands of light years. A notable example is the antennae galaxies, NGC 4038 and NGC 4039, where two spiral galaxies are nearing the final stages of their merger. The streams of material emanating from these galaxies, resembling giant antennae, are the result of interactions that have spanned hundreds of millions of years. Gravity has created a dramatic scene, transforming two separate galaxies into a dynamic tableau of radiant trails. Beyond shape distortions, one of the most remarkable phenomena during galactic interactions is starburst activity. The interactions compress interstellar gas clouds, sparking intense star-forming regions where millions of young stars are born in a short time. These regions shine brightly, with the blue light of hot, young stars, marking a highly active phase in a galaxy's life cycle. The antennae galaxies are a prime example of this event. The merger has triggered unprecedented star formation on a massive scale, producing dense and luminous star clusters that highlight a phase of explosive stellar activity. As interactions progress, galactic mergers often become the final outcome. This process unfolds over billions of years, with two galaxies gradually merging into a larger one. The resulting galaxy often appears irregular during its early stages, retaining traces of both progenitor galaxies, including star-forming regions and long streams of material. Over time, gravitational forces stabilize the structure, transforming the merged galaxy into a more familiar shape, such as an elliptical or spherical form. Giant elliptical galaxies like M87 in the Virgo cluster are likely the result of multiple such mergers. Interactions between galaxies are not just breathtaking spectacles, but also play a pivotal role in the universe's evolution. They reshape galaxies, spark star formation, and contribute to the creation of new galaxies. By studying these interactions, scientists can not only better understand the history of galaxies in the universe, but also predict their future evolution. These interactions open a new chapter in the universe's story, where each galaxy plays a significant role in the grand cosmic drama. Amidst the vast universe, where many galaxies teem with vigorous star-forming activity, there exist galaxies considered dead, places where star formation has ceased. These galaxies are like silent relics, where the dim light of old stars tells the story of a once brilliant past, while their cold surfaces attest to the depletion of the raw materials needed for rebirth. The characteristics of dead galaxies are easily recognizable. The light they emit is often weak and lacks the diverse colors of active galaxies. Instead, their glow primarily comes from old stars that have existed for billions of years, the witnesses of previous stellar generations. The primary reason for their inability to form new stars is the lack of interstellar gas and dust, essential ingredients for star formation. Without these vibrant energy sources, dead galaxies become cemeteries of stars, where aging stars gradually fade away in isolation, with no younger generations to replace them. The causes of a galaxy's death can stem from various cosmic phenomena. One common cause is interactions or collisions with other galaxies. These events often disrupt a galaxy's internal structure, ejecting interstellar gas and dust into space. As a result, the galaxy loses the material needed to form new stars, halting star-forming activity. Additionally, supermassive black holes at the cores of galaxies play a significant role. These black holes often emit intense radiation and energy, heating interstellar gas to the point where it cannot condense into new stars. This phenomenon, known as quenching, is a prevalent reason why many galaxies gradually become inactive. A prime example of a dead galaxy is Messier 87, AM87, a massive elliptical galaxy in the Virgo cluster. M87 is famous for its supermassive black hole, whose first ever image was captured by the Event Horizon Telescope in 2019. This black hole is not only a scientific highlight, but also a contributing factor to the galaxy's death. The material jets and radiation emitted from the black hole have inhibited star formation, turning M87 into a massive yet quiescent galaxy. This characteristic is common among many elliptical galaxies in large clusters, where most stars formed in the early universe, and significant activity has since ceased. Nevertheless, dead galaxies remain scientifically invaluable. They are precious time capsules that allow astronomers to study the history of the universe and the evolution of galaxies. Understanding how galaxies transition from active, vibrant states to silent stillness provides critical insights into the universe's life cycle. Moreover, dead galaxies help us explore the long-term effects of major cosmic events, such as galactic collisions and supermassive black hole activity, on galaxy formation and survival. Although no longer producing stars, dead galaxies are fascinating objects in the universe. They not only demonstrate the diversity of galaxies, but also remind us that everything in the universe has a life cycle, from a brilliant beginning to a final quiet state. These galaxies, with their cold and tranquil beauty, continue to inspire scientific inquiry and spark the desire to uncover the mysteries of the cosmos. In the vast universe of hundreds of billions of galaxies, some stand out not only for their unique beauty, but also for their dramatic tales of interaction and transformation. Galaxies M86 and NGC 4438, two main characters in the Virgo cluster, not only reveal their fascinating forms, but also unveil the captivating struggles unfolding in the depths of space. Galaxy M86, a prominent member of the Virgo cluster, is one of the rare galaxies exhibiting a blue shift, a phenomenon uncommon in an ever-expanding universe. While most galaxies move away from each other due to the expansion of space, M86 is swimming against the tide, heading closer to us. This phenomenon not only intrigues with its unusual nature, but also provides critical insights into gravitational forces and galactic interactions within the intergalactic medium. Despite being approximately 52 million light-years away from the Milky Way, M86 is moving toward us at a remarkable velocity of 244 kilometers per second. This is among the highest recorded blue shift velocities in astronomy. This phenomenon occurs not because M86 is defying the universe's expansion, but because it is strongly influenced by the gravitational forces of other galaxies and matter in the Virgo cluster. This gravitational pull draws M86 toward the cluster's center, making it a vivid example of the complex interactions between galaxies and their surrounding intergalactic environments. However, this upstream journey is fraught with challenges. As it moves through the dense, hot gas of the Virgo cluster, M86 encounters significant resistance, losing a substantial amount of its interstellar material. Streams of ionized hydrogen gas trailing behind the galaxy are clear evidence of this process. These gas trails, resembling smoke trails left in space, not only illustrate M86's high velocity, but also demonstrate how galaxies interact with their surroundings. This loss of interstellar material, known as ram pressure stripping, occurs when a galaxy moves rapidly through the intracluster medium, causing its gas and dust, key ingredients for star formation, to be stripped away. As a result, M86 gradually loses its star-forming capability, potentially transitioning into an aged and quiescent galaxy in the future. The blue shift of M86 is not only intriguing due to its rarity, but also holds significant scientific value. It provides deep insights into the relationship between galaxies and the intergalactic medium, helping scientists better understand how galaxies interact, lose material, and evolve over time. Studying M86 also sheds light on how galaxies in large clusters, like the Virgo cluster, evolve and influence one another. As M86 loses a substantial portion of its interstellar gas, it may undergo profound changes in its structure and activity. These changes could lead to the collapse of its spiral arms, the decline of star-forming activity, and ultimately, its transformation into a more quiescent elliptical galaxy. Furthermore, studying the ionized gas trails behind M86 provides valuable data on how matter is transported and dispersed in the intracluster environment. These gas trails not only reveal the galaxy's movement history, but also offer crucial information about the physical properties of the intergalactic medium. These clues help scientists reconstruct the broader picture of galaxy cluster formation and evolution. M86's journey is not merely a fascinating phenomenon, but also serves as a natural cosmic laboratory. By studying M86, astronomers gain insights into the blue shift phenomenon and uncover the profound effects of gravitational forces and the intergalactic environment on galaxies. Each movement of M86 is a testament to the universe's dynamism and complexity, a universe constantly evolving and recording its wondrous stories in the light of its stars. Galaxy NGC 4438, another member of the Virgo cluster, is a vivid testament to the destructive potential of cosmic interactions. Initially a balanced and radiant spiral galaxy, NGC 4438 now bears a distorted shape, resembling a colossal scar in space. This severe deformation is thought to result from powerful interactions with Galaxy M86 or other nearby galaxies. NGC 4438's peculiar form not only captivates with its unusual appearance, but also narrates the profound effects of gravitational forces in the universe. The dramatic transformation in NGC 4438's structure is primarily due to the impact of these interactions. The strong gravitational forces between NGC 4438 and other galaxies in the Virgo cluster disrupted its original shape. The once balanced, well-defined spiral arms have been stretched and warped into irregular forms, creating a completely new appearance. Additionally, a significant amount of interstellar gas and dust, essential materials for star formation, has been ejected from the galaxy, depriving NGC 4438 of much of its vibrancy. As a result, this galaxy now resembles a relic of cosmic collisions, where gravity showcases its overwhelming power. Another remarkable phenomenon arising from this interaction is the formation of filaments of material. These strands of gas and dust connecting NGC 4438 and M86 are clear imprints of their interaction. These filaments not only evidence the exchange of matter between galaxies, but also form unique, rare structures in the universe. These threads highlight the connection between the two galaxies and provide scientists with valuable opportunities to study how matter moves and distributes within the intergalactic medium. By analyzing these filaments, astronomers can reconstruct interaction events that occurred millions of years ago, unlocking the complex history of galaxies in the cluster. Despite its severe deformation, NGC 4438 remains a critical object in astronomical research. Its distortion tells a story not only of gravitational forces, but also of the alteration of internal physical processes within the galaxy. With the loss of a significant amount of interstellar gas and dust, NGC 4438's star-forming capability has diminished, leading to substantial changes in its structure and activity. These changes also illuminate how gravitational forces can impact factors such as material distribution and internal dynamics within a galaxy. Research on NGC 4438 provides valuable insights into how galaxies evolve, especially when interacting with their environment. Moreover, NGC 4438's deformation demonstrates how galaxies constantly change in a dynamic universe. From a radiant spiral galaxy, it has transformed into a distorted and complex entity. evidencing the power of gravitational forces and the role of the intergalactic medium in shaping galaxies. The scars on NGC 4438 are not merely traces of intense interactions, but also vivid proof of the universe's continuous transformation. NGC 4438's journey from a balanced spiral galaxy to a distorted and unusual form is not merely a tale of destruction, but also an opportunity to understand how galaxies change and evolve over time. With each deformation, it provides a deeper perspective on the universe and the powerful forces that shape it. Although no longer perfect, NGC 4438 shines as a precious witness to the dramatic and awe-inspiring phenomena in space. The relationship between galaxies M86 and NGC 4438 extends beyond their proximity in the Virgo cluster, manifesting in a striking phenomenon: streams of ionized gas connecting the two galaxies. These streams not only exemplify the strength of gravitational forces, but also tell a story of intricate and profound interactions between galaxies within the intergalactic medium. The gas streams linking the two galaxies are the direct result of intense interactions between M86 and NGC 4438. Strong gravitational forces have pulled interstellar matter, including gas and dust, from one galaxy to the other, forming bridges of material connecting these colossal entities. These ionized gas streams, faintly glowing in the dark expanse, serve as clear evidence of the close encounters between galaxies. They are not only traces of past events, but also provide critical insights into how galaxies influence each other on a large scale. By studying these streams, scientists can reconstruct the history of interactions, gaining a clearer understanding of how gravity shapes the structure and activity of galaxies. These streams are not merely bridges of material, but also have a profound impact on the evolution of both galaxies. M86, with its remarkable blue shift velocity, is losing a significant amount of interstellar gas through these interactions. In contrast, NGC 4438 may receive some of this material, potentially triggering new star formation in regions enriched by the transferred gas. This is a quintessential example of how galactic interactions can be both destructive and regenerative. While M86 gradually loses its star-forming resources, NGC 4438 might experience a burst of star formation, highlighting the dual nature of galactic interactions. This exchange of material not only alters internal structures, but also reshapes the future of both galaxies. This phenomenon also underscores the formidable power of gravity in shaping the universe. Gravity not only governs the motion of galaxies within clusters, but also has the ability to alter their structures and activities. Even within a dense environment like the Virgo cluster, home to hundreds of galaxies, close interactions are potent enough to create significant changes. The ionized gas streams connecting M86 and NGC 4438 are a reminder that the universe is not a collection of isolated celestial objects, but a complex network where every component can influence another. Gravity acts as the conductor, orchestrating the relationships among these cosmic players in an ever-changing symphony. Furthermore, the existence of these ionized gas streams provides invaluable opportunities to study the intergalactic medium, the space between galaxies where complex physical processes occur. By analyzing these streams, astronomers can gather information about the temperature, density, and chemical composition of the intergalactic environment, deepening our understanding of how galaxies interact and evolve. These delicate yet powerful gas filaments also shed light on the role of gravity in transporting and dispersing matter on a cosmic scale. The connection between M86 and NGC 4438, manifested through ionized gas streams, is a vivid testament to the dynamism and interconnectivity of the universe. These faint material trails are not only evidence of cosmic interactions, but also tell a profound story of how galaxies cooperate and compete in their evolutionary journey. With every study, we move closer to unraveling the mysteries of a universe where each galaxy plays an essential role in a grander cosmic tapestry. In the vast universe of billions of galaxies, some stand out like colossal torches, shining brightly and emitting immense amounts of energy. These galaxies not only astonish scientists with their extraordinary power, but also offer rare opportunities to understand the formidable strength of supermassive black holes. What makes active galaxies so exceptional? Active galaxies are extraordinary objects in the universe, where their central cores, commonly known as active galactic nuclei, AGN, emit colossal amounts of energy, surpassing the combined energy of all the stars within the galaxy. These galaxies are not only dazzling, but also serve as natural laboratories, where scientists can study extreme and rare physical phenomena. The defining feature of active galaxies is the presence of a supermassive black hole at their center. This black hole is not dormant, but acts as a monster, voraciously consuming material from its surroundings. As gas, dust, and even stars approach the black hole, they are drawn into an accretion disk, a rotating disk of matter surrounding the black hole. During this process, friction and extreme temperatures heat the material, causing it to emit vast amounts of energy before disappearing into the black hole. This intense interaction is the source of the energy radiated by active galactic nuclei, with a brightness that can outshine the combined light of billions of stars in the galaxy. The energy emitted by active galaxies extends beyond visible light, covering a broad spectrum of electromagnetic radiation, including X-rays, gamma rays, and radio waves. This diversity makes active galaxies ideal targets for modern telescopes. For example, the Hubble Space Telescope provides clear images in visible light, while Chandra and other X-ray observatories explore the high-energy regions near the AGN. These observations enable scientists to better understand the mechanisms driving active galactic nucleus luminosity and the interactions between supermassive black holes and their surroundings. The primary distinction between active galaxies and ordinary galaxies lies in their energy sources. In a typical galaxy, most energy originates from starlight. However, in active galaxies, the AGN can contribute up to 90% of the galaxy's total energy output. This makes their cores extraordinarily bright, often overshadowing the rest of the galaxy, appearing as isolated luminous points in space. This characteristic makes AGNs cosmic lighthouses, observable from billions of light-years away. Beyond their brilliance, active galaxies are pivotal pieces in the puzzle of cosmic evolution. They provide insights into how supermassive black holes form and grow, and their role in shaping galactic structures. Supermassive black holes not only consume matter, but also release powerful energy in the form of galactic winds or plasma jets, which can influence surrounding gas clouds and even inhibit new star formation. This phenomenon, known as AGN feedback, can regulate galaxy evolution, transitioning them from vibrant activity to more quiescent phases. A notable example of an active galaxy is Messier 87, M87, where scientists captured the first-ever direct image of its central supermassive black hole in 2019. These observations not only confirmed the black hole's existence, but also demonstrated the remarkable synergy between theoretical models and modern technology in cosmic research. In summary, active galaxies are not only brilliant torches illuminating the universe, but also keys to unlocking profound questions in astronomy. From unraveling AGN luminosity mechanisms to understanding the role of black holes in galaxy evolution, AGNs remain central to cosmic exploration. They tell tales of the universe's extremes while opening new frontiers for human discovery. The immense energy of active galaxies originates from one of the most intense phenomena in the universe: the process of matter falling into the supermassive black hole at their center. This process not only produces dazzling light, but also generates powerful phenomena, illustrating the harsh and intricate forces of physics at play in the cosmos. When materials such as gas and dust from the surrounding regions approaches the black hole, it does not fall straight in, but forms a swirling accretion disk. The matter in this disk moves at extreme speeds under the strong gravitational influence of the supermassive black hole. As it spirals inward, particles collide, compress, and create intense friction, raising temperatures to millions of degrees Kelvin. This heat causes the accretion disk to emit vast energy across various wavelengths, from visible light to X-rays and ultraviolet radiation. This mechanism explains the brilliance of active galaxies, making them cosmic beacons visible from billions of light-years away. The luminous energy of active galaxies extends beyond the accretion disk to include explosive phenomena. The high temperatures in the disk not only produce visible light, but also generate strong emissions in shorter wavelengths, such as X-rays and ultraviolet rays. This explains why active galaxies are often prominent in observations made with modern telescopes, especially X-ray observatories like Chandra or the Hubble Space Telescope. This light not only characterizes AGN brilliance, but also provides critical data about the extreme environments surrounding supermassive black holes, where physical forces operate at their peak. However, the light emitted by the accretion disk is only part of the story. Some active galaxies also unleash tremendous energy through plasma jets ejected from the black hole's poles. These jets, traveling at nearly the speed of light, can extend millions of light-years, far beyond the galaxy itself. They form colossal and striking structures like radio lobes, commonly observed in blazars or quasars. These plasma jets not only demonstrate the immense power of supermassive black holes, but also profoundly impact the surrounding intergalactic medium, generating shock waves and heating vast gas regions. The energy-emitting processes of active galaxies exemplify the interplay between gravity and cosmic dynamics on a grand scale. The gravitational force of the supermassive black hole shapes the motion of surrounding material and drives extraordinary high-energy phenomena. These interactions not only define the luminous nature of AGNs, but also offer opportunities to study how gravity and radiation operate in the universe's most extreme conditions. Beyond their luminosity, active galaxies provide valuable insights into how the universe's fundamental forces shape galactic structures and activities. They reveal the absolute power of supermassive black holes and their role in regulating galaxy evolution. Even from billions of light-years away, the brilliance of active galaxies provides vital clues, gradually unraveling the universe's deepest mysteries. Active galaxies are a unique group in the universe, classified into various types based on their energy characteristics and structures. Among them, Seyfert galaxies, quasars, and galaxies emitting massive plasma jets are the most prominent examples, demonstrating the immense power and complexity of physical processes at their cores. Seyfert galaxies are one of the most common and recognizable types of active galaxies. They feature a bright central core while retaining their spiral or elliptical structures, creating a harmonious blend of high-energy activity and traditional galactic forms. Their energy primarily radiates invisible and ultraviolet light, making them easily observable with optical telescopes. A prime example is Galaxy NGC 1068, M77, located about 47 million light-years from Earth. As one of the brightest and most studied Seyfert galaxies, NGC 1068's core hosts a highly active accretion disk, emitting enough energy to illuminate its entire central region. Observations reveal complex interactions between its central supermassive black hole, accreted material, and jets from the galactic core. While Seyfert galaxies are more common, quasars are considered the brightest and most energetic active galaxies in the universe. Their cores radiate hundreds of times the total energy of the rest of the galaxy, often observed at vast distances, representing early universe galaxies. A notable example is 3C273, the first quasar discovered, located about 2.4 billion light-years away. With brightness billions of times greater than the Sun, 3C273 symbolizes the immense power generated by intense interactions between supermassive black holes and surrounding matter. This quasar exemplifies energy production on a scale sufficient to illuminate the universe's darkest regions. Beyond Seyferts and quasars, some active galaxies stand out for emitting enormous plasma jets from their cores. These jets, traveling near the speed of light, arise when charged particles in the accretion disk around the supermassive black hole are accelerated by powerful magnetic fields. A striking example is M87, a giant elliptical galaxy in the Virgo cluster, famous for its central supermassive black hole. M87 emits not only immense energy from its core, but also a plasma jet extending about 5,000 light-years. This jet provides deep insights into how supermassive black holes interact with their environments, demonstrating the incredible power of gravity and magnetic fields in the universe. Examples like NGC 1068, 3C273, and M87 not only illustrate the diversity of active galaxies, but also offer critical data for testing astrophysical theories. Observing and studying these galaxies allows scientists to better understand AGN mechanisms, the role of supermassive black holes, and the impact of high-energy jets on the intergalactic medium. Active galaxies are not only luminous lighthouses in space, but also keys to unlocking major questions about the universe's formation and evolution. In summary, Seyfert galaxies, quasars, and plasma jet galaxies like M87 represent some of the most fascinating and challenging phenomena in astrophysics. They demonstrate the power of gravity and magnetic fields while opening doors to explore unknown corners of the universe. Each observation brings humanity closer to unraveling the profound mysteries of the cosmos. When we look up at the night sky, we see only a tiny fraction of the universe. But with the James Webb Space Telescope, JWST, humanity has opened a new door to peer deep into the universe's past and uncover the secrets of the origins of stars, galaxies, and even planets. JWST is not just a scientific tool, but a time machine taking us back to the universe's earliest days. The James Webb Space Telescope, JWST, is not merely an astronomical observatory, but a symbol of scientific progress and the desire to unravel the universe's greatest mysteries. Designed as a superior successor to the Hubble Space Telescope, JWST promises to take a giant leap in our ability to explore the cosmos, opening new chapters in the history of astronomical observation. As the most advanced telescope ever built, JWST was designed to overcome the limitations of previous telescopes while offering observational capabilities far beyond any tool humanity has ever used. While Hubble primarily operates in the visible and ultraviolet light spectrums, JWST is optimized for infrared observation. This provides a significant advantage, allowing JWST to look deeper into space and further back in time. Light from the first galaxies and stars, emitted over 13 billion years ago, has been red-shifted across billions of light-years due to the universe's expansion. Optical telescopes like Hubble cannot detect this light, but JWST, with its sensitivity to infrared wavelengths, can capture it in detail. This capability makes JWST an essential tool for studying the early stages of the universe. Exploring the universe's early stages is one of JWST's primary scientific objectives. Scientists hope that JWST will allow them to see the first stars and galaxies formed after the Big Bang, when the universe was only a few 100 million years old. This was the era when the universe's large structures began to emerge, from primordial hydrogen clouds to the first galaxies. By studying light from this period, JWST will illuminate how the universe evolved from its initial chaotic state into the complex system of galaxies, stars, and planets we see today. This data will not only help scientists better understand the history of the universe, but also provide profound insights into our origins, from the fundamental components that created the first stars to the formation of planetary systems like our solar system. Expanding planetary research is another crucial mission for JWST. Its exceptional infrared observation capabilities enable JWST to study not only distant galaxies, but also exoplanets, planets outside our solar system. One of JWST's remarkable abilities is to analyze the atmospheric composition of exoplanets by observing starlight passing through their atmospheres. This technique can detect the presence of molecules such as water vapor, methane, or carbon dioxide, potential signs of life. This represents a major step forward in answering humanity's biggest question: does life exist elsewhere in the universe? JWST is not just a tool for observation, but a bridge connecting humanity to distant worlds that may harbor conditions suitable for life. JWST's significance lies not only in its technological prowess, but also in its symbolic value. It embodies the power of innovation and global collaboration as scientists, engineers, and organizations from numerous countries joined forces to build a tool capable of answering fundamental questions about the universe. It represents humanity's unceasing curiosity and desire to understand the origins of the cosmos, life, and our place in the vast expanse of space. With its ambitious goals and groundbreaking technology, JWST is not just a telescope, but a symbol of hope, reminding us that we can uncover the unknown and open new horizons for humanity. To achieve its ambitious goals of exploring the universe, the James Webb Space Telescope, JWST, was designed with cutting-edge technology, making it a pinnacle of engineering excellence in scientific history. Every detail of JWST was optimized to deliver unprecedented observational capabilities, unlocking access to the farthest reaches of space. JWST's massive primary mirror is one of its most outstanding features, surpassing the capabilities of previous telescopes. With a diameter of 6.5 meters, significantly larger than Hubble's 2.4-meter mirror, the mirror has a light-collecting area over 6 times greater. Composed of 18 segments of ultralight and durable beryllium, the mirror is coated with a thin layer of gold just a few micrometers thick to maximize infrared reflectivity. This combination allows JWST to collect light from objects billions of light-years away, including the first stars and galaxies in the universe's history. Its large size and sophisticated design not only deliver unparalleled detail, but also bring us closer to understanding the origins and evolution of the cosmos. JWST's advanced sun shield is a unique innovation that helps the telescope overcome one of the greatest challenges of infrared observation: heat. Because infrared light is thermal radiation, any heat source, including the telescope itself, can interfere with data collection. To address this, JWST is equipped with a 5-layer sunshield made from Kapton, an ultra-light and durable material capable of reflecting nearly all heat. This sunshield keeps the telescope's instruments at a frigid -233 degrees Celsius, 40 Kelvin, cold enough to eliminate thermal noise. This design enables JWST to operate in the harsh environment of space, ensuring that measurements and images achieve the highest accuracy. The telescope's location is another critical factor in optimizing its performance. Instead of orbiting Earth like Hubble, JWST is positioned at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth. This location, where the gravitational forces of the Earth and Sun balance with the telescope's centrifugal force, allows JWST to maintain a stable orbit with minimal fuel consumption. At L2, the telescope remains behind Earth relative to the Sun, shielding it from sunlight and thermal interference. This setup minimizes disturbances and ensures a continuous view of the deep cosmos. These groundbreaking technical features demonstrate JWST's superiority and reflect humanity's relentless creativity and determination to push technological boundaries. From its impressive primary mirror to its cutting-edge sunshield and ideal location at L2, every aspect of JWST was meticulously planned to fulfill its revolutionary mission, uncovering the universe's greatest mysteries. It is not merely an astronomical observatory, but a testament to international collaboration and scientific ambition, heralding a new era of cosmic exploration. The ability to observe in the infrared spectrum is one of the James Webb Space Telescope's, JWST, most significant advantages, allowing it to explore the universe's most hidden regions that previous telescopes could not reach. Through this technology, JWST has opened a window to the most obscured corners of space, providing profound insights into the universe's history and nature. Detecting faint light and redshift phenomena is one of the primary reasons why infrared wavelengths are vital in modern astronomical observation. As light from the universe's earliest galaxies and stars travels through space, the continuous expansion of the universe stretches its wavelength, shifting it from visible light to the infrared spectrum. This phenomenon, known as redshift, renders the most distant objects invisible to traditional optical telescopes. With its sensitivity to infrared light, JWST can detect faint signals from celestial objects billions of light-years away, taking us back to the universe's infancy shortly after the Big Bang. This breakthrough enables scientists to study how the first stars and galaxies formed, and how matter organized itself during the universe's early stages. Piercing through cosmic dust is another crucial capability JWST offers. While cosmic dust plays a significant role in star and planet formation, it often obstructs optical telescopes by blocking light from objects behind it. Infrared light, with its longer wavelength, can penetrate dense dust clouds, revealing regions of space previously hidden. This ability is particularly useful for studying nebulae where young stars are born. With JWST, scientists can directly observe the earliest stages of star formation, providing a deeper understanding of how stars evolve and influence their surrounding environments. Applications in planetary research are another promising frontier for JWST. Its infrared observation capabilities extend beyond distant galaxies to the analysis of exoplanets, planets outside our solar system. By observing starlight passing through these planets' atmospheres, JWST can identify their chemical compositions, including the presence of water vapor, methane, carbon dioxide, and other compounds. This information is vital for assessing the potential for life on distant worlds. JWST offers significant hope in answering whether Earth is the only inhabited planet in the universe, ushering in a new era of exploring other worlds. With its ability to observe in the infrared spectrum, JWST has become the most powerful tool for uncovering the farthest reaches of the universe and unraveling its unanswered mysteries. From studying the light of the first stars to analyzing the atmospheres of exoplanets, JWST not only provides invaluable scientific data, but also expands humanity's vision, connecting us to the universe's distant history. Thanks to JWST, the hidden corners of space and time are now within reach, ready to tell their vivid stories. From billions of light-years away, light from the universe's earliest galaxies and stars is being unveiled through the keen eyes of the James Webb Space Telescope, JWST. With advanced technology, JWST not only brings us closer to the era of the Big Bang, but also provides discoveries that redefine our understanding of the universe's evolution. One of the most significant scientific achievements of the James Webb Space Telescope, JWST, is its ability to observe galaxies at the edge of the universe, offering the deepest insights into the earliest chapters of the cosmos. With cutting-edge technology, JWST transcends the boundaries of time and space, expanding our understanding of how the universe formed and evolved. JWST's ability to transcend time and space makes it a groundbreaking tool in astronomy. With a 6.5-meter primary mirror and the capability to observe infrared light, JWST can capture light from galaxies over 13 billion light-years away. The light we see from these galaxies originated during the universe's infancy, just a few 100 million years after the Big Bang. This represents a monumental leap forward, allowing scientists to study the first galaxies formed from primordial matter like hydrogen and helium during the era when the universe's fundamental elements began to take shape. By peering into these early moments, JWST helps humanity rewind time, providing a clearer picture of how the universe transitioned from chaos to order. The unprecedentedly detailed images from JWST have transformed how we observe and understand distant galaxies. Unlike previous observations that revealed only faint points of light, JWST delivers sharp images, exposing the intricate structures of early galaxies. Data from JWST reveals compact galaxies with dim light, considered the seeds of larger galaxies seen today. Beyond discovering new galaxies, JWST aids in understanding how galaxies merge, interact, and evolve over time. These seemingly small galaxies tell the story of how massive galaxy clusters and large-scale cosmic structures formed. For the first time, scientists can trace the distribution of matter in distant galaxies, enabling more accurate models of galaxy evolution. Contributing to cosmology, JWST's observational capabilities not only test existing hypotheses, but also provide robust evidence for developing advanced cosmological models. Previously, it was believed that galaxies in the universe's early stages existed in simple forms. However, observations from JWST show that even in infancy, galaxies existed in various shapes and sizes, indicating a more complex formation and evolution process than previously thought. These findings expand our understanding of how galaxies emerged and offer critical clues about the formation of large-scale structures in the universe, from galaxy filaments to superclusters. Additionally, studying distant galaxies sheds light on the role of dark energy and dark matter in shaping the universe. JWST's ability to observe galaxies at the universe's edge marks not only a revolutionary step in astronomy, but also a journey through time to uncover the universe's first moments that shaped everything we know today. Thanks to JWST, secrets hidden in the most distant galaxies are now revealed, helping us understand not just the origins of the universe, but also humanity's place and role in this vast cosmos. In addition to observing distant galaxies, the James Webb Space Telescope, JWST, has made a groundbreaking contribution to cosmic research by allowing humanity to meet the universe's first stars, population 3 stars, for the first time. These stars, previously known only in theory, hold the key to understanding how the early universe was shaped and evolved. Discovering population 3 stars is one of JWST's primary scientific goals, and the initial results have not disappointed. Population 3 stars are considered the first generation of stars in the universe, forming shortly after the Big Bang, when the universe was only a few 100 million years old. Unlike today's stars, population 3 stars were composed entirely of light elements like hydrogen and helium, as heavier elements like carbon, oxygen, and iron had not yet formed through nuclear processes. With its ability to detect faint infrared light, JWST has enabled scientists to find evidence of these stars for the first time, opening up an unexplored era. The light we see from population 3 stars is the light emitted by the universe's first stars, taking us back in time to explore the origins of everything in the cosmos. The role of the first stars in cosmic history cannot be overstated. These massive, high-temperature stars had short lifespans, often lasting only a few million years before ending in powerful supernova explosions. When population 3 stars exploded, they dispersed heavy elements like carbon, oxygen, and iron into space, creating the essential materials needed for forming subsequent generations of stars and planets. Thanks to these elements, new galaxies and planets, including our solar system, were able to form. Population 3 stars were not only pioneers in creating matter in the universe, but also laid the foundation for the current cosmic structure. With JWST, scientists have found evidence of these first stars and gained deeper insight into their role in shaping the universe as we know it today. The discoveries enabled by JWST extend even further. Beyond detecting population 3 stars, JWST provides detailed data on how these stars interacted with their surroundings. This includes studying primordial nebulae, where the first stars were born from clouds of hydrogen and helium. By analyzing these nebulae, scientists can better understand how population 3 stars emitted light and transformed their environment. Notably, data from JWST also aids in studying the ionization process, a period when population 3 stars ionized surrounding gas, transforming the universe from a dark state to one illuminated by starlight. This information not only clarifies our understanding of the early universe, but also offers opportunities to test key cosmological hypotheses. The discovery of the universe's first stars not only illuminates one of the earliest chapters in cosmic history, but also provides profound insights into how matter and energy interacted to form larger structures, from galaxies to galaxy clusters. Though population 3 stars no longer exist today, their legacy is indelibly imprinted on the formation of matter and the universe's structure. With JWST's help, humanity is closer than ever to uncovering and decoding the greatest mysteries about the universe's origins and our own. One of the James Webb Space Telescope's, JWST, groundbreaking scientific contributions is its ability to analyze radiation from primordial gas clouds, the direct remnants of the Big Bang. These clouds, long considered hypothetical, have now been revealed in detail by JWST, providing new insights into how the universe's first matter coalesced to form early galaxies. The remnants of the Big Bang are the source of these primordial gas clouds, primarily composed of hydrogen and helium, the two lightest and simplest elements in the periodic table, created immediately after the Big Bang. These gas clouds are not only the universe's first raw materials, but also contain valuable clues about how the earliest galaxies and large structures formed. The light emitted from these primordial clouds carries information about their temperature, density, and chemical composition, serving as a natural record of events in the universe's infancy. With its ability to analyze infrared light, JWST can detect and decode these faint signals, enabling scientists to delve into the universe's earliest moments. This is a remarkable achievement, as the light from primordial gas clouds has been highly redshifted over billions of years of cosmic expansion, rendering them invisible to traditional optical telescopes. Reconstructing the process of matter coalescence is one of JWST's significant contributions through its analysis of primordial gas clouds. Data from the telescope reveals how clouds of hydrogen and helium were drawn together by gravity, forming denser regions that became precursors to the first galaxies. These gas clouds were not only influenced by gravity, but also interacted complexly with high-energy radiation from early stars. This process ionized the surrounding clouds, altering the dynamics of matter and triggering the formation of new stars. Through JWST, scientists can observe this process in detail for the first time, reconstructing how the first galaxies were born and developed in the early cosmic environment. This is a groundbreaking advancement, shedding light on critical stages in the universe's evolution. Building and refining cosmological models is another essential application of analyzing primordial gas clouds. Data collected by JWST not only supports existing theories about galaxy formation, but also provides crucial experimental evidence to test and refine cosmological models. In particular, these observations help answer significant questions about the roles of dark energy and dark matter in shaping and driving the evolution of large-scale cosmic structures. Understanding how primordial gas clouds coalesced into galaxies offers a comprehensive view of the universe's evolution and opens new research avenues into how more complex structures, from galaxy clusters to superclusters, formed and endured over time. Primordial gas clouds, though seemingly simple and modest, form the foundation of all the large structures we observe in the universe today. Thanks to JWST, scientists have seen and analyzed them in detail for the first time, expanding humanity's understanding of how matter was organized and formed during the universe's earliest stages. This is not only a scientific breakthrough, but also a journey of discovery, taking us back to our origins, where primordial gas clouds marked the beginning of everything. The James Webb Space Telescope, JWST, is not just a tool for observing the universe, but also a key to unlocking the greatest mysteries of space and time. From analyzing light from distant galaxies to studying the atmospheres of exoplanets, JWST is opening new doors for science and technology. One of the most significant applications of the James Webb Space Telescope, JWST, is its ability to analyze light from galaxies billions of light-years away from Earth. This capability not only allows humanity to explore the hidden corners of the universe, but also provides detailed insights into how galaxies form, evolve, and contribute to the broader picture of the universe's history. The advanced spectroscopy technology of JWST forms the foundation for its ambitious mission. Equipped with state-of-the-art spectrometers, JWST can analyze light from distant galaxies by breaking it down into its constituent wavelengths. This process is akin to how a prism separates light into a rainbow, but with far greater precision and range. From this spectral data, scientists can determine the chemical composition of galaxies, including the proportions of elements such as hydrogen, helium, carbon, and oxygen. Additionally, the spectra provide information about the ages of stars within the galaxies, their rates of expansion, and levels of activity. This data not only helps reconstruct how galaxies formed from primordial matter after the Big Bang, but also sheds light on their complex evolutionary stages over billions of years. Measuring redshift is one of JWST's most remarkable achievements when analyzing light from distant galaxies. Redshift occurs when light from a galaxy is stretched toward the red end of the spectrum due to the universe's expansion. This phenomenon serves as a crucial yardstick for determining the distance and expansion rate of galaxies. By measuring this effect, JWST enables scientists to accurately calculate the positions of galaxies in space and identify the time when the light left the galaxy, effectively letting us look back into the past. This data provides robust empirical evidence to test current cosmological models, such as the Lambda CDM model, while offering deeper insights into the universe's history and structure. Redshift measurements also help pinpoint the evolutionary stages of the universe, from the formation of the first galaxies to the development of today's massive galaxy clusters. Exploring hidden corners of the universe is an invaluable benefit of JWST's ability to observe in the infrared spectrum. This capability allows JWST to see through dense clouds of dust, regions inaccessible to traditional optical telescopes. These are the sites where early galaxies are forming and evolving, holding critical clues about how matter gathered and organized during the universe's initial stages. Through these observations, JWST has illuminated the roles of dark matter, which holds galaxies together, and dark energy, which drives the universe's expansion. These discoveries not only broaden our understanding of the universe's complex physical processes, but also provide foundational data for building new models that can more accurately predict the future evolution of the universe. Analyzing light from distant galaxies turns JWST into a true time machine, taking humanity back to the universe's earliest moments. The light from galaxies billions of light-years away carries ancient messages, telling the story of galaxy formation and evolution and their role in the universe's overall progression. Through JWST, we can uncover hidden secrets in space and construct a more comprehensive picture of the universe's history, from its chaotic beginnings to the intricate development we observe today. One of the groundbreaking and promising applications of the James Webb Space Telescope, JWST, is its ability to study the atmospheres of exoplanets. With advanced technology, JWST not only helps explore the characteristics of distant planets, but also opens up opportunities to search for planets that could support life, one of humanity's greatest unanswered questions. Observing light passing through the atmospheres of exoplanets is the core method JWST uses to investigate the chemical and physical properties of worlds beyond the solar system. When a planet transits its host star, an event known as a transit, the starlight passes through the planet's atmosphere before reaching the telescope. JWST, equipped with cutting-edge spectrometers, analyzes this light by breaking it down into its component wavelengths. Each chemical compound in a planet's atmosphere absorbs light at specific wavelengths, creating a unique chemical fingerprint. This allows scientists to detect molecules such as water vapor, methane, carbon dioxide, and oxygen. Key elements not only for determining atmospheric conditions, but also for hinting at a planet's potential habitability. This marks the first time we can observe and analyze exoplanet atmospheres at this level of detail. Searching for signs of life is one of JWST's most crucial goals in studying the atmospheres of exoplanets. Molecules like oxygen, ozone, or methane are not only indicators of chemical activity, but could also be directly linked to life. On Earth, oxygen and ozone are byproducts of photosynthesis, while methane is a byproduct of various biological processes. Detecting these molecules in the atmosphere of a distant planet could suggest the presence of life, or at least conditions suitable for it. With its exceptional sensitivity, JWST can observe and identify these chemical signatures even on small planets located tens of light-years away from Earth. This represents a major leap forward, bringing humanity closer to answering the question of whether we are alone in the universe. Expanding the scope of the search is another advantage JWST offers, thanks to its superior infrared observational capabilities. Beyond Earth-like planets, JWST also studies gas giants, worlds with diverse atmospheric layers and unique physical conditions. Scientists believe that while the surfaces of these planets may not be conducive to life, their upper atmospheric layers could provide stable environments that support non-traditional life forms. This capability broadens our understanding of the diversity of planetary systems and potential life forms in the universe. Additionally, JWST helps investigate planets in the habitable zone, the distance from a host star where liquid water can exist, as well as planets beyond this zone, where unique conditions might give rise to entirely new forms of life. Studying exoplanet atmospheres makes JWST a pioneering tool in the search for life, while also expanding humanity's understanding of our place in the vast cosmos. By uncovering atmospheric compositions and linking them to planetary structures and conditions, JWST is gradually building a comprehensive picture of how planets, and potentially life, develop under varying circumstances. With every planet studied, JWST not only provides valuable scientific data, but also ignites greater hope and curiosity about existence beyond Earth. Is Earth unique? And if not, where else might we find life in this vast universe? The James Webb Space Telescope, JWST, is not only a leading instrument for studying galaxies and exoplanets, but also plays a vital role in uncovering the formation and evolution of planetary systems in the universe. With its unparalleled observational capabilities, JWST provides detailed and unique insights into the processes that create new worlds, from protoplanetary disks around young stars to fully formed giant planets. Observing protoplanetary disks around young stars is one of JWST's primary missions in planetary science. Young stars, particularly those only a few million years old, are often surrounded by massive disks of dust and gas. These disks are where planets begin to form through the accumulation and collision of material. Previously, studying these disks in detail was challenging due to dense dust clouds obscuring them. However, JWST's infrared capabilities allow scientists to see through these layers of dust, providing clear images of their structures and chemical compositions. This enables a better understanding of how planets form, from tiny dust grains coalescing into massive planets. Additionally, JWST helps uncover the distribution of matter within protoplanetary disks, shedding light on the role of gravity and dynamics in creating complex planetary systems. Exploring giant planets is another promising application of JWST in planetary science. Gas giants like Jupiter and Saturn in our solar system, or hot Jupiters beyond it, offer valuable insights into how planetary systems develop. By analyzing the reflected light from these planets, JWST can determine their atmospheric compositions, including hydrogen, helium, methane, and ammonia. Spectral data also reveal physical characteristics such as temperature, pressure, and gas distribution within the atmospheres. This not only enhances our understanding of the structure of giant planets, but also provides clues about their interactions with host stars and other planets in their systems. Observations from JWST may even detect signs of moons or dust rings around these planets, opening up new possibilities for studying the diversity of planetary systems. Reconstructing planetary histories is another crucial contribution of JWST. By observing young stars and newly formed planets, JWST helps scientists recreate the early stages of planetary formation. This data provides a detailed picture of how primordial material from dust and gas clouds coalesced to form planets, and how factors like radiation from host stars and the influence of dark matter affected this process. Through JWST, we can trace how a planetary system transitions from its initial chaotic state to stability and growth into mature worlds with stable orbits and unique atmospheres. These insights not only shed light on the origins of the solar system, but also extend research to other planetary systems, offering a more comprehensive view of planetary evolution across the universe. JWST's applications in planetary science go beyond exploring distant planetary systems. They also deepen our understanding of the solar system's origins. From studying protoplanetary disks to analyzing giant planets and reconstructing planetary histories, JWST has provided a wealth of data to unravel the mysteries of how planets are born and evolve. More importantly, these discoveries open up the possibility of answering bigger questions about the existence of Earth-like systems and the potential for finding life in the vast universe. With JWST, we are not only closer to understanding our place in the cosmos, but also expanding the boundaries of human knowledge about the worlds beyond.